electrons as they transition from one energy level to the next. We'll also talk about quantum numbers, and we will talk about electron configuration. I think periodic table towards the end of the chapter. So let's get into it here. So a lot of what we will sort of be talking about is the idea of electrons as they sort of transition from one energy level to the next. So if you have an electron, it goes from a lower energy level to a higher energy level. As we talked about with the conservation of energy, there's really no loss of energy along the way. So it obviously takes a certain amount of energy for that electron to get up into a higher energy level. When it starts to get up to that higher energy level, one of the things in chemistry, right, is things in high energy levels is not really ideal. Things don't really want to be in the highest energy levels. They much rather be in a much lower state of energy. It's a much more stable situation. So what typically happens a lot of times, we will get these electrons that will try to work their way back down in terms of energy to a lower energy level, a little bit more of a stable sort of situation. Because we do have this sort of conservation of energy, the only result of that is that energy to do that is released by the atom. And if that energy is released by the atom, as we'll talk about, is sometimes released in the form of a wave. And if that wavelength of that energy corresponds to something, say, in the visible part of the spectrum, then we see colors. Pretty much what happens there with fireworks. When they shoot off the fireworks, you have obviously explosions, creates a lot of energy for the electrons and those elements that are in those fireworks. Electrons jump to higher energy level, they come back down, you see the pretty colors, you go, ooh, ah, and all that kind of stuff, right? A couple of weeks, apparently, we will see that, I suppose. All right, so we do see different colors because as we will talk about, depending on the elements that are present, the electrons are transitioning from different energy levels, and they will give off, again, different wavelengths of energy as they transition down, which will result in, sort of the different colors that you see. Not all electron transitions will, for example, be in sort of the visible part of the spectrum where you would see color. They could be outside of that spectrum where you wouldn't see color. Maybe you feel heat or something like that. But again, what we can visually see is a result of those guys sort of transitioning. So one of the ways that basically energy moves through space is in the form of waves. And there's some characteristics of waves. We have the wavelength, the speed, and the frequency. So if we have a wave that's basically moving, as we will see, kind of from both peaks or both troughs, that's the wavelength, which is usually abbreviated as lambda. The frequency is basically, how fast a wave passes a particular point every second, or how often it passes a particular point every second. We also have the amplitude of the wave, from the baseline to the top there. And the speed obviously is how fast it's moving. A lot of times that's going to be in meters per second. So the wavelength is again lambda, is the distance between two peaks or two troughs. The frequency, which is new, which is what that symbol is, not really a V, is the number of waves per cycle per second that pass through a particular point. And one of the characteristics of waves that move in sort of electromagnetic radiation is the speed of light, which is 3 times 10 to the 8. I personally use the more rounded number of 3 times 10 to the 8 meters per second, and that's the speed of light. So we could use this equation here, which relates wavelengths to frequency, and that is the speed of light is equal to the wavelength times the frequency. We could also rearrange this equation, and if we want to solve for the wavelength, that would be the speed of light divided by the frequency. And if we wanted the frequency, it would be a similar rearrangement there, speed of light divided by the wavelength. The units, obviously, of speed of light is meters per second. The typical units here of wavelength is going to be meters when you use it in here. And frequency has typical wavelengths of 1/seconds or reciprocal seconds. Another terminology that's sometimes used for frequency is a reciprocal second is the same as a hertz. So a hertz is also used a lot for frequency. And again, it basically is the same as basically a reciprocal second. So those are common sort of units that are used. Again, if you use this equation, you need to make sure that your wavelength is in meters. It's not in some other unit like centimeters or nanometers or something like that, so that all the units properly cancel out. Any questions on that there? So once again, as I mentioned, you do need to know formulas. So, make sure that you know these formulas. Let's take a look at one. Why don't you give it a try? Calculate the wavelength of red light with a frequency of, what we got there, 4.62 times 10 to the 14. And why don't we do it in nanometers, which is oftentimes what color light there is, like red light, invisible part of the spectrum. Nano is 10 to the minus 9. Okay, let's take a look. So obviously we could use our equation there. Our C is equal to our wavelength times our frequency. In this case, we are solving for wavelength. So our wavelength would be our speed of light divided by our frequency. We do have our frequency there. So our wavelength would be 3.0 times 10 to the 8 meters per second divided by our frequency of 4.62 times 10 to the 14 reciprocal seconds. Again, here we want to make sure that we use our exponent buttons. So 3 exponent button 8 divided by 4.62 exponent button 14, going to give us 6.49 times 10 to the minus 7. The units here would be meters, as the reciprocal seconds and the seconds there would cancel each other out. Here we do want nanometers. And again, when we see nano like this, that means in this particular case, in 1 nanometer, there is 10 to the minus 9 meters. Again, not the other way around. So we would take 6.49 times 10 to the minus 7 meters. We want to get rid of meters. So the 10 to the minus 9 meters on the bottom, 1 nanometer. Again, that is basically 1 times 10 to the minus 9. If you want to put it into your calculator that way, you can. We will divide it by here. Basically 1 times 10 to the minus 9, going to get us 649 nanometers here. Questions on that calculation? Let's try another one here. I think that's the one we just did. That's good. All right, so calculate the wavelength of a radio signal if you should turn your dial to 100.7 megahertz. Mega is 10 to the 6th. So you could do this one in meters. It's fine. All right, let's take a look at this one here. So obviously we're going to use the same equation there. We got our speed of light equal to our wavelength times our frequency. In this case, we're going to solve for the wavelength. Good news is kind of same rearrangement there. Now, remember the speed of light there is our 3 times 10 to the 8 meters per second. And this is basically off of seconds, that's megahertz. So I'm going to first convert my frequency into reciprocal seconds or hertz by itself and not megahertz. So again, the mega here is that would be in 1 megahertz. There is 10 to the 6 hertz. So again, that is the proper way to use that. And that means that if we take our 100.7 megahertz and divide it by, not that, 10 to the 6 hertz, and 1 megahertz. Our megahertz here will cancel, and we will end up with 100.7 times, basically 1 times 10 to the 6th, gonna get us 1.007 times 10 to the 8 hertz. That is also the same thing as 1.007 times 10 to the 8 reciprocal seconds. So again, they are basically the same thing. At this point, I have it in the right units so that it will really cancel out correctly there with our speed of light seconds. So we're going to do a little wavelength action there, 3 times 10 to the 8 meters per second divided by 1.007 times 10 to the 8 reciprocal seconds. Once again, those guys are going to cancel out and going to leave us with meters when it's all left over. Once again, using our exponent button there, we're going to hit something like a 2.98 meters in this case. Any question on that? And that is typical what you find for radio waves, kind of in that range is typically the wavelength that you see there. And that is a much larger wavelength than what you saw with the red light, the visible light there, that in the previous problem. Any questions on the calculation there? Okay, so let's talk a little bit more about these waves. And again, this is really how energy is sort of transmitted through space in the form of these waves, and definitely what's occurring as electrons transition from one energy level to the next. And there is an association in terms of the wavelength and its frequency and the energy of waves, depending on what you have going on. So let's take a look at some of those there. So when we look at wavelengths, when we have a longer wavelength, that usually means you have a lower frequency. And that usually results in a lower energy for that wave. So if you got a wave that's sort of a long wavelength, it's just sort of meandering across space, if you will. And that's different than if we have a wave that has a much shorter wavelength. Usually will result in a higher frequency, and that usually has higher energy associated with it. So like... So as we can see here, these are 3 sort of different colors of waves, or waves that produce 3 different types of colors. We have red, green, and blue. So even among the different colors that we can see in the visible part of the spectrum, there is a difference in terms of the energy associated with those waves. Here we can see that the wavelength for our red is much longer than, say, our wavelength for our green, and even longer, obviously, than our wavelength for our blue light there. And that would mean in this case that this red would be sort of lower in energy. This bluish light here, which has the shortest wavelengths of these 3s, which would be the higher guy there in energy. And obviously the green would fall somewhere between those 2 as well. So when we think about colors, there's the Roy G. Biv, right? The red, orange, yellow, green, blue, indigo, violet. There is a difference in terms of the energy that comes off when those waves are there. Now, as we talk about sort of energy, again, the transition of energy, when an electron obviously goes from a lower state of energy to a higher state of energy, it has to absorb all that energy, right, to allow it to gain enough energy to transition from one energy level to the next. So it's sort of an endothermic process in terms of the atom for those electrons to absorb the energy and go up. Again, as the electrons sort of relax back down to a lower state of energy, it's more exothermic for the atom. It's going to release that energy, right, as it transitions down to allow the electrons to come back down to a lower state of energy. And as we're talking about, depending on sort of where that wavelength comes off of as it's sort of transitioning, it may fall somewhere in what's known as the electromagnetic spectrum. And the electromagnetic spectrum is basically the sort of the different areas in terms of energy that comes off in terms of waves. And on this side, we have wavelengths of like 10 to the 4. On this side here, we have 10 to the minus 12. So clearly over here, this is a much longer wavelength. and we would expect a much lower energy as opposed to the other end of the extreme here. That is a much shorter wavelength, and it would expect a higher energy on that side of the spectrum. So over here to the right, we got things like radio waves and things like that, which is why, you know, it's not too bad to listen to your radio on the way in to class. Kind of not a lot of energy. As we move to the left here, we are increasing in energy. So we have microwaves next. Microwaves have enough energy to just kind of spin water molecules really fast and heat up your pizza in 3 minutes, right? So you could eat it. Coming next to it is infrared, a little bit more energy. That is where we feel heat that usually comes off of things. It usually falls in that infrared sort of spectrum. After the infrared spectrum, we have the visible spectrum here. So that is the visible spectrum. And that is where we see our colors of, like I said, Roy G. Biv, right? And here, these guys are typically in the visible part of the spectrum because they are really small wavelength. A lot of times are given in nanometers. Everybody else, a lot of times are given more in just meters, but definitely in here, we will see the wavelengths given in nanometers. We have our different energy associated with these colors. So as we saw on the previous slide, down this way towards the red would be lower in energy. It has a much longer wavelength than, say, more of the purple end of the spectrum, where we have a higher energy happening here. So again, even between the colors here, we do have a difference in terms of the energy associated with those waves that come off. Obviously, that is what we see, right, in the visible part of the spectrum. So if we have any transitions, say, of electrons that give off energy in the form of waves that fall in this region, we will see the colors. By the way, the color that we see is really the complementary color to the light being absorbed, right? So we see like a red solution. It's actually more of a greenish color kind of being absorbed, and that's, you know, why we see it as red. After our visible part of the spectrum, we get some more energy happening there. We have our ultraviolet, right? That's why we put sunblock on, right? So we do not get so toasted, right, and burnt in the sun. We then have X-rays, more energy. Why they put a lead vest on you, right, usually, and leave the room when they shoot the X-ray, right, because they do not want to do that. And we have gamma rays, as we talked a little bit about in the previous chapter. Gamma rays are really just kind of pure energy. They're radioactive rays, and they are very, very high in energy sort of rays. So energy is increasing, obviously, as you go to the left on this picture, decreasing as you go to the right. Longer wavelength on the right-hand side, where radio waves are, shorter wavelength there on the left-hand side. Now, as I mentioned before, as, say, electrons transition, it doesn't necessarily always has to fall in the visible part of the spectrum, that wavelength. Again, it could fall outside of that. The result of that is, obviously, you would not see a color sort of associated with it. Again, you might feel heat or something else of that nature. You do need to know the electromagnetic spectrum here. You do need to know it in the sense of which ones are, say, higher in energy, longer wavelength, shorter wavelength. I won't ask exactly where everybody breaks off in terms of exact numbers or anything like that, but you do need to be able to put it in order based on that sort of criteria: higher energy, lower energy, wavelengths, frequency as well. And that includes the colors. So you do need to know the differences in terms of the colors, in terms of their energies as well. Any questions on that? Obviously, in terms of frequency, we would have a lower frequency to the right, a much higher frequency to the left there, where we have the higher energy as well. Yeah. You just know the order. Again, I'm not going to ask you, where exactly microwave wavelength is, or, anything like that, but you do need to be able to put it in order, like I said, in terms of longer, shorter wavelengths. So the general sort of orders as you see on here. Yeah. Other questions? That's a pickle. All right. Good talk. I thought it really was a good talk. All right. So energy can be gained and only lost in certain multiples of energy, I think is what that probably should say. And that is sometimes referred to as the idea of a quanta of energy. And the idea really of a quanta of energy is the idea that Some, for example, electrons will only gain and lose enough energy to basically go from one energy level to the next. They will never find themselves sort of in between. So they always lose these things. And as we'll see, they lose it in terms of E is equal to H times the frequency here, which is a quantum of energy. So you can kind of think of it a lot of times as like a staircase sort of model. Sometimes people describe it. Yeah. So when we're walking upstairs, for example, you typically have enough energy, right, to get to this stair. You know, you have enough energy to get to this stair or that stair, or even coming down, right? Same idea. You have enough energy to get back down to each of those stairs. You never usually walk a stair and go, I'm just going to kind of stop in between because I'm just kind of tired. I can't make it to the next step. So that's the same thing with sort of electrons as they transition. They will gain or lose enough energy to fully transition from one energy level to the next. And just like when people walk stairs, sometimes people can maybe do 2 stairs at a time, right? 3 stairs at a time. Same thing with electrons. They could either, you know, gain enough energy, maybe to go up 2 or 3 energy levels or down 2 or 3 energy levels at a time. But again, you'll never find an electron kind of hanging out in between energy levels. And that's the idea, sort of the idea of quantized energy. We'll talk a little bit about continuous energy or spectrum. And a continuous sort of spectrum where everything comes off at once. It's more like a ramp where pretty much if you're walking up a ramp, you could stop anywhere along the way on the ramp, right? And you'll be fine. And that's sort of a continuous sort of emission or a spectrum that comes off, as opposed to a more quantized version that we see with electrons and elements. The result of this, as we'll talk about, is they give off these nice specific sort of lines of energy at specific wavelengths where these transitions basically occur. So energy is quantized, and electromagnetic radiation, again, is a stream of particles or photons, and that is what is sometimes referred to as electrons transition back down. They give off a photon of light. And a photon of light obviously is that energy associated that's coming off from an atom in this particular case. Now to calculate that, as I just scribbled over it. So we could calculate the energy of a photon by taking E is equal to H times the frequency, as I mentioned before. H is Planck's constant. And that is 6.63 times 10 to the minus 34 joules times seconds. So that is a constant value. And obviously the frequency here is just like we were talking about before, our reciprocal seconds. So if you take joules times seconds times reciprocal seconds, you end up with joules as the units associated with the energy here. As I scribbled through it, we will put it back together here. So the earlier equation that we saw, the C is equal to the wavelength times the frequency. If we solve for the frequency, which is C divided by the wavelength, we could take our equation here, E is equal to H times frequency. That means H times C divided by the wavelength. So putting both of those equations together allows us a couple different ways that we could actually solve for the energy of a wavelength of a wave coming off of light. If we know just the frequency, we could times it by Planck's constant, and that will give us our energy in joules. If we just know the wavelength, we could use H times C, and both of those are constants. So H again being the Planck's constant, C being the speed of light, and divided by the wavelength. So just knowing one of those two things about the wave, either the frequency or the wavelength, will allow you to calculate the energy associated with that wave. Obviously here using this equation, our wavelength does need to be in meters because of the speed of light is in meters per second. So again, you got to watch those units. You got to make sure you do the conversion and get it into meters. And again, that does come up a lot, obviously, in the visible part of the spectrum where it's usually given in nanometers. So again, that nanometers, the 10 to the minus 9 conversion is used a lot to take it from nanometers to meters, and sometimes the opposite way around. Any questions on that there? So energy has mass, and that's Einstein's equation, E equals mc squared. M is mass, c is the speed of light. And there's always this sort of dual nature of light that's oftentimes talked about when we talk about these sort of things. And the idea here is that light can have both wave-like properties and also properties that are similar to particles. So that's what the dual nature of light sort of referring to. So it can have obviously a mass and associated energy associated with it, and it can move as like a stream of particles, but it also has wavelength and wave-like sort of characteristics associated with it. And that gives us really the two types of sort of spectrums that we come across. As I mentioned a second ago, something like a continuous spectrum is typically what we see when white light is passed through a prism. It basically contains all the wavelengths of visible light, and things like elements that are basically heated or energy added to it gives a more distinct sort of spectrum, and that's more of a continuous spectrum. And as I mentioned before, sort of our staircase example where things are on certain energy levels, that will result in these specific lines that come off as specific wavelengths that are associated with those electrons doing those transitions. Again, a more continuous spectrum, you kind of will see, very badly drawn here, but like colors, everybody coming out, you know, sort of at once. There's really no distinction between exactly the wavelength where these things come out. One thing about elements is that they do give these line spectrum where we have specific lines that occur at specific wavelengths, and every element gives its own sort of distinct line spectrum. So depending on the lines that you see and where they fall out, the colors that you see, you can basically identify what element you're dealing with just based on the lines that are present. You'll do this tomorrow with a spectroscope. It has a prism in it. It will separate it out. You'll be able to see these sort of distinct lines that will occur at specific wavelengths that correspond really to electrons transitioning from one energy level to the next. Now, the significance of hydrogen is only certain energies are allowed for the electron in the hydrogen atom. And again, that electron is that quantized sort of version. So it's only going to be on perhaps the first energy level, second energy level, third. It will only do those transitions from one energy level to the next. And why is it significant that the color emitted from the hydrogen atom is not white? It's because it's got this quantized energy basically, and we got this specific transitions occurring for the electrons in hydrogen. So one of the ideas there, as we'll talk about, is sort of the Bohr model of the atom, where, you know, we have an electron that is transitioning downward, say from that energy level. Maybe the electron's up here and is transitioning further down. And depending on how far they sort of transition as to what we see in terms of comes off. And in the case of hydrogen, we see these four sort of distinct lines that come off at different wavelengths and different colors because of this quantized energy, rather than seeing everything coming off as the case sort of stop along the way. Again, it will not stop along the way. It will get to one energy level or the next. And that is the Bohr model of the atom and the Bohr theory of the hydrogen atom, which is sometimes referred to as sort of the planetary model. And the idea there is sort of what I just drew. You have sort of your nucleus, and then you have these different sort of rings, which are sometimes referred to in the Bohr model as orbits. And they're at different energy levels, like n is equal to 1, which is the ground state. And that is the lowest in energy. And anything above that, like n equals 2 through, say, 7, are higher energy states, are levels. And these are what are sometimes referred to as excited states. So, you know, if this is, say, like our n equals 1 or n equals 2 and so forth, n equals 3. Again, in his sort of model, he had sort of the electrons really sort of circling about the nucleus, fixed in these orbits. So they just kind of go around in pretty little circles as they may transition from one energy level to the next, resulting in sort of the energy lines that we see associated with hydrogen. Now, he was a theory here in terms of Bohr, and as we talked about earlier, theories, are thought of as maybe being correct or incorrect. And what we found was that it works really well for hydrogen that has one electron, but as you move away from sort of hydrogen with multiple electrons involved, it doesn't really hold up very much. And as we'll talk about, we will transition away from this idea of the planetary model, where again, just going to rotate in nice pretty circles, like you could almost put your finger there and know eventually it'll come back around the circle, right? And you could hit the electron, to an idea more quantum mechanical model where we do not really know exactly at any given point in time where a particle like an electron is or how it's moving. And that's what is sometimes referred to as the Heisenberg uncertainty principle, that the more you know about one thing, about the location, say, of a particle, the less you know about how it's traveling and vice versa. So we will move away from orbits and this sort of model into the more orbital model that we do for electrons. Now, when we see the lines, for example, in hydrogen, they can be explained by sort of the Bohr theory, because it is the transition that occurs here. And as you can see here, for example, our red guy is transitioning from, say, the third energy level to the second. Our green sort of line that we would see on the spectrum is transitioning from the fourth to the second. And our blue line here, right, is transitioning from the fifth to the second. Based on the colors that we see, we should also know the amount of energy associated with them. Which color did we say had the most energy out of those three? It was the blue, right? And we could see that the transition for the blue one is going from 5 to 2, right? A much larger transition in terms of energy levels, going to require a lot more energy, right, to do that, or be released as it's coming down in terms of energy. The lowest in energy, as we saw, was red, right? And we could see the transition for red, for example, is only 3 to 2, which is just one energy level, which means it's going to give off a lot less energy. It's going to result in a longer wavelength that's going to occur as those transitions occur. So just by looking at the colors that you see, you can make a estimate as to the energy that's being released, or how far perhaps an electron is transitioning. Any questions on that there? So again, in just more of a circular matter here, which is our orbitals here, and again, our Bohr model, which we will be moving away from, obviously, as it doesn't hold up much past hydrogen. Now, for a single electron, we can basically calculate the energy associated with that transition of the electron moving from one energy level to the next. And we could use this equation here, which is the change in energy is equal to minus 2.178. Some people will use 2.18 and round it. And this is what is sometimes referred to as Rydberg's constant. So that is Rydberg's constant, that number there. And it is equal to, not equal to, but it is multiplied by 1 over n squared final. N squared final, n is the principal quantum number, by the way. So n is the principal quantum number. It is a fancy word for energy level, basically. There are 4 quantum numbers, which we'll talk about a little bit later on in this chapter, and one of them is n, which is basically the energy level associated with an electron. So that's basically where the electron ends up, minus 1 over n squared, where the electron started, what energy level it basically started at, and that will give you the change in energy. Since this is still our change in energy, this is also related to the other equations that we saw. This is equal to h times the frequency, Planck's constant. This is also equal to hc over the wavelength, right? So you can also obviously associate with the electron as it's transitioning. If you know the change in energy, you can figure out the wavelength associated with it. You can also figure out the frequency associated with the light that's coming off as the electron transitions. It is really important in a couple of things when you do these calculations, which is this: when we calculate something like energy or the change in energy like we have here, as we talked about yesterday, The sign is important. If it is a negative value for delta E or E, that is going to be exothermic, right? Which means heat and energy should be released. And if you end up with a positive value for delta E, that's going to be endothermic, which means heat and energy is going to be absorbed. It is really important when you do these calculations here that you keep the sign for the energy part. So you do need to keep the sign for the energy part, because again, I tell somebody whether or not it is giving off energy or absorbing energy. As we just talked about, we would expect a change in energy as the electron goes from a higher energy level to a lower energy level to be positive or negative. As it goes from higher energy to lower, it should be negative, right? Again, the atom's going to have to give off that energy, right, and release it, be exothermic. And as the electron goes, say, from a lower energy level, right, to a higher energy level, it should be a positive number as it needs to gain it. So if we were talking about an electron transitioning from, say, the third energy level to the second, or going from the second energy level to the third energy level, will the actual number be different in terms of the energy for that electron? It will not. It'll be the same number, right? But the sign will be different in terms of the energy, depending on which way the transition is happening. So you could have a negative, whatever it is, or a positive, but it will be the same amount of energy is required to do the transition going up or going down. And again, that's the quantized part of the energy there. Again, the difference here is the sign. So it's important when you do calculate to leave the sign there if it is negative. With that being said, when we calculate something, perhaps with those numbers involving frequency or wavelength, those guys should be positive values. So if you do end up with a negative value for your energy, you should just make it a positive value when you go do the rest of the calculations. So you do not end up with a negative wavelength or negative frequency. So those guys should be positive numbers. So when you do calculate, these guys should be positive numbers. And our energy here could be negative or positive. Okay, so, but you definitely should get rid of the negative side when you do the rest of the calculations, so you don't end up with any of those weird calculations. So, any questions on that there? All right. So the model correctly fit, again, the quantized energy that we do see with the hydrogen atom, as they have these nice circular orbits around the electron. But the electron becomes more tightly bound. Its energy is more negative relative to its reference point, and the electron is brought closer to the nucleus as energy is released from the system. So, you know, as we sort of release energy, everybody gets brought in closer, and sort of the normal sort of attractive forces is basically what this is talking about. As we talked about, obviously the nucleus is positively charged, right? Electrons are negatively charged. So there is going to be that attractive forces is going to bring everybody closer in basically to the nucleus. So Bohr's model, as I mentioned, is not correct in all aspects. Again, it works really well to describe sort of the four lines that you see in hydrogen, but it does sort of fall apart as you have more electrons involved, because as you sort of pile in more electrons, you do get some other things that start to happen, right? Electrons are negatively charged, so as you pile in more electrons near each other, right, do they really want to be near each other? They do not, right? Because they're the same charge. So you get a lot of electron repulsions that kind of come into play as you sort of pile in, obviously, more and more electrons, say, into the atom. So as we talked about, Bohr's model of the atom, not correct, you know, in all aspects, works really well for hydrogen, but does fall apart. Electrons do not move around the nucleus in this sort of circular pattern like sort of described there in Bohr's model. And as we'll talk about, moving away from that, we have this more sort of quantum mechanical model where electrons move in this really random sort of pattern about the nucleus. The best that we could do is talk about probability of finding an electron. And again, we sort of transition, as we'll talk about, into electrons being these theoretical sort of models of what are referred to as orbitals, rather than these nice circular orbits. And we sort of transition away from that and moving into this more orbital sort of model and uncertainty. All right, so let's do some calculations here. What color of light's emitted from an excited electron as they transition from the fifth to the second, the fourth to the second, the third to the second? Let's calculate the change in energy. Let's do the wavelength for each of those. Let's do the frequency for each of those. And let's do the wavelength in nanometers. There we go. And the energy will be in joules. All right. Okay, let's take a look, see how you're doing. So we have several different sort of transitions occurring here. So this electron in the first one starting at the fifth energy level, right? Higher energy to our second energy level. So let's take a look at that one first here. So we're going from n equals 5 to n equals 2. So obviously here we would want to use the equation we just saw there that had the Rydberg's constant in it. That allows us to calculate the change in energy associated with it, as that's the only information given to us. Minus 2.18 times 10 to the minus 18 joules. Again, that is Rydberg's constant. And we're going to do our 1 over n squared final minus our 1 over n squared initial. And obviously here, this is our initial here. That is our final. And we will put it in. So minus 2.18 times 10 to the minus 18, 1 over basically 4 as we square the 2, right? Minus 1 over 25, right? As we square the 5 there. And if we do all that, kind of clean it up here, we're going to take 1 divided by 4 minus 1 divided by 25. I'm going to times it by 2.18 to the negative 18. And that's going to give us here negative 4.58 times 10 to the minus 19 joules here, right? Here we did get a negative value, which does make sense as it's transitioning from higher energy to lower. It's got to give off that energy exothermic. So our energy should be a negative value, and we should keep the negative here when we give the answer for our energy. Any questions on that so far? Yeah. The 425 is basically n squared, final state, initial. So these are our initial, which basically is 5 squared, right? 25. And then that was our final, which is 2 squared, which would give you 4. Yeah. Yep. Other questions? Okay. So now that we have the energy, we really can hit either one in terms of wavelength or frequency, whichever one you kind of want to do first. Remember that this is also equal to basically h times our frequency, which would allow us obviously to calculate the frequency by just using that. H again is Planck's constant, which is a constant value that you always have, 6.63 times 10 to the minus 34 joule seconds. So if we did that, basically we're taking each E times H times the frequency. The frequency here would then be E divided by H. And that would give us here 4.58 times 10 to the minus 19 joules. Here I'm going to get rid of the negative so I don't end up with a negative frequency here. We're going to divide it by our constant, 6.63 times 10 to the minus 34 joules times seconds. Here the joules will cancel in this case. And if we do that, again, making sure to use your exponent buttons would be a good idea. And divided by 6.63 to the negative 34, going to give us something like, we'll call it 6.91 times 10 to the 14. The units here are going to be reciprocal seconds, not seconds. 1 over seconds will be our unit when we're done here. At this point, again, you really do have a couple of options. You could use the original equation that we saw, C is equal to the wavelength times the frequency, since we have both of those at this point. You could also still use the energy one. You could use the E is equal to HC divided by the wavelength, which we also have, obviously, both of those values as well. So again, they both should pretty much give you the same answer, maybe slightly different if you did a little bit of rounding, but you should pretty much get the same answer. So I'm just going to roll with this one here. So our wavelength in this case would be C divided by our frequency, which we just calculated. So that's going to be our speed of light. And we'll do our frequency. And that will get us 3 to the 8 divided by, I'll just use the rounded numbers here. Gets us 4.34 times 10 to the minus 7. The units here will be meters at this point, and we are looking for nanometers. So squeeze it in somewhere. Let's see. We'll go over here. Maybe I'll get rid of this. So the last thing we'd want to do here, since we are looking for the nanometers, is to do our nanometer conversion. So we'll take 4.34 times 10 to the minus 7 meters. Again, a nanometer is 10 to the minus 9 meters in 1 nanometer. And that will get us 434 nanometers in this case. Any questions on that one there? That is at 434, somewhere in the bluish range, probably, in terms of the color associated with it, if you look back on that spectrum that we saw earlier. All right, let's take a look at the next one. Next one, we're transitioning, I think, 4 to 2. So we'll do that one. So next one, we're doing n equals 4 to n equals 2. Again, that's going to be our final. That's going to be our initial here. So again, based on what's given to us, we pretty much have one option, the same option we did previously. We're going to take our 2.18 times 10 to the minus 18, or Rydberg's constant, 1 over, again, our final squared and our initial squared. So put in our numbers in, 2.18 times 10 to the minus 18 joules. In this case, our final is 2. So that's going to be, again, 2 squared is 4. So 1 over 4 minus our initial, which is 4 squared, which is 16 in this case. And putting that into our calculator would be a much better idea. So we got 1 divided by 4 minus 1 divided by 16. I guess what I was going to say is make sure you square it, not times it by 2, which sometimes people will do, times 2.18 to the minus 18. That's going to give us some energy here for this wave coming off at 4.09 times 10 to the minus 19 joules. Once again, it is going to be negative, as it is going from a higher energy level to a lower. Again, at this point, you do have your options. For example, if you wanted to mix it up, you could use E is equal to HC over the wavelength and hit the wavelength first if you wanted to. That means that the wavelength here would be HC divided by E. H being a constant, 6.63 times 10 to the minus 34 joule seconds. Our speed of light, 3 times 10 to the 8 meters per second. And our energy, once again, we're going to drop the negative sign here, so we do not get a negative wavelength. So if you chose to take this pattern, should get you there as well. That's going to give us 3 to the 8 divided by 4.09 to the minus 19. That will get us 4.86 times 10 to the minus 7. Units here, seconds will cancel, joules will cancel, meters is what's left over. Once again, we'll do our conversion into nanometers. 10 to the minus 9 meters is a nanometer. And that's going to get us 486 nanometers. At that point, we could get to our frequency. Again, however you want to do it, could also, again, use the E equals H times the frequency. Given our frequency, E divided by H. And that would be, again, dropping the negative 4.09 times 10 to the minus 19 joules divided by 6.63 times 10 to the minus 34 joules times seconds. And that's going to get us it looks like 6.17 times 10 to the 14. Once again, reciprocal seconds is our units, as the joules here will cancel out. And that's, I don't know, greenish in terms of color. Question? I'm sorry, say again. Does it? It's final minus initial. Should be. Yeah. Other questions? It would be that if it was basically if it was the opposite, if it was going the opposite way, it would be that. And really the only thing that would change here, right, is the energy would become positive, right, as it would be going in that direction. Yeah. H is a constant, it's Planck's constant, 6.63. H and C are constants. So that's why you can use this a lot of times. You want to, you know, if you just know the wavelength, for example, you can figure out the energy because H and C are constants. So you always have those numbers available to you. And in this case, you could also use it the opposite way there if you know the energy to get the wavelength. Other questions? All right, one last transition, I think was it 3 to 2? 3 to 2. All right, so let's do the 3 to 2 transition here. So this is our initial, right? This is our final. And again, we'll start it the same way as we did the previous ones. Our change in energy going to be minus 2.18 times 10 to the minus 18 joules. 1 over our final, which would be 4, and minus 1 over our initial 3 squared is 9 in this case. And that's going to give us 1 divided by 4 minus 1 divided by 9 times 2.18 to the minus 18 gives us 3.03 times 10 to the minus 19 joules. That's negative. And again, we would expect it to be negative as it's transitioning down in energy. And now we can just calculate everything else there. We'll do our frequency first. So our frequency would be E divided by H, which again is a constant. Dropping the negative here gives us our 6.63 times 10 to the minus 34 joules times seconds. Probably helps to put the right number in. Try that. All right, save that there. We got 4.57 times 10 to the 14 reciprocal seconds. And C is equal to the wavelength times the frequency we could use to get to the wavelength. Wavelength is C divided by the frequency. And that would give us 3 times 10 to the 8 meters per second divided by 4.57 times 10 to 14 reciprocal seconds. Going to give us 6.56 times 10 to the minus 7 meters. Doing our conversion again to take it to nanometers. 10 to the minus 9 meters is a nanometer. Going to give us 656 nanometers here. I don't know, orange, red-ish type color. And again, as you can see, there's a couple different pathways that you could do these problems, obviously, depending on sort of which way you go. They, again, should pretty much give you the same answer regardless of which way you go. Yeah, we dropped to negative just for practical reasons. Wavelength and frequency should always be positive numbers. Otherwise, obviously, if you leave it in there, you'll end up with a negative number. That's really the straightforward answer to that. But we do want to make sure we keep the negative if it happens to be negative for the energy, because it's important to let people know that that's an exothermic sort of process with that negative sign. And if you leave it as a positive number for energy, you're basically saying it's the opposite transition happening. It's basically absorbing that much energy. So definitely for energy and just general chemistry calculations, anything with energy should always keep the sign. If it's negative or positive, you should always make sure you have that negative or positive there for energy sort of values. But definitely wavelengths and frequencies are usually positive numbers. So the easy answer is just really just kind of convert it to a positive number if you need to. Yeah. Well, there are multiple paths. Like, for example, this way here to get the wavelength, I use this equals the wavelength times frequency. You could, just like I did in the previous one, I think, use E equals HC over the wavelength. So all those should get you away, should all get you to the same answer, you know, depending on which way you choose. So there are sort of multiple ways you can kind of do some of these problems and stuff. Yeah. And really, which way you choose is really sort of based on the information that you have in front of you. So whatever way you want to do it. In this case, we actually have enough information to go multiple ways, so it doesn't really matter. Other questions? Okay. So clear, you need to be able to do all this. Yes, all these calculations. Okay. And again, you do need to know these formulas as well. All right. So obviously we got some good practice here, calculating wavelengths, frequencies, and energy associated with these waves. By the way, to answer the question, right, and our transitions here, for this last one, going from 3 to 2, we had a wavelength of 656. Let me zoom in case you missed it. For our 4 to 2, we had a wavelength of 486. And for our 5 to 2, we had a wavelength of 434. I don't remember what the original question was asking. Was the longest wavelength? Yeah. So the one that had the longest wavelength was the last one, I believe. It was our last transition, had the longest wavelength, corresponds to orange and red. The one with the most energy should be which one? Yeah, so the one with the most energy is our 5 to 2, which should have the smallest wavelength, which is what we see out of those three, right? So our 5 to 2, which had the longest sort of haul, should result in more energy being sort of given off. Ended up with 434, which had the shortest wavelength, and our guy that had the shortest transition, which should give off less energy, right, had the longer wavelength, which is what we see here. Yeah. Any questions on that? Okay. All right. All right. So as we've been talking about, when these waves, energy is sort of transmitted as waves, and this dual nature of light, these sort of waves can have particle-like function and wave-like function. A guy by the name of Broglie came up with the idea that particles could exhibit wave-like character. It could kind of be like a stream of particles, much like a wave. And he predicted that wavelengths of a particle are inversely proportional to its momentum. And because it is so small, the wave character of electrons is significant. He sort of came up with the idea of like, and it's an interesting thing, he actually didn't do any experiments. It was all sort of theoretical. And later on, people did experiments, sort of proved him sort of correct. But the idea of sort of a standing wave, if you will. And in a standing wave, there's sometimes points along the way, which are sometimes referred to as nodes, where there's no amplitude, basically, right? So it's sort of this flat out there. And if it's kind of like a guitar string, right? If you pluck a guitar string, right, it's attached to the guitar, but it will still make the wave, right? You can kind of see it, right? And it's like a standing wave. It can't really detach from the guitar because it's bolted in. And it's the same idea here with our electrons, although they are traveling around the nucleus. They sort of are attached to the nucleus by that attractive force, which creates a sort of standing wave as they are traveling around to the nucleus, as you would have if you plucked like a guitar string, and you can kind of see the wave. So you could calculate what is sometimes referred to as the de Broglie wavelength, which is used to calculate the wavelength of things that are like particles, like electrons or golf balls, whatever it may be. And to calculate the de Broglie wavelength, the wavelength in meters is equal to h times the seconds here, divided by the mass, divided by the frequency. And h is Planck's constant. So again, that is our Planck's constant, 6.63 times 10 to the minus 34 joules times seconds. This joules part right here is what we saw the other day, is this part of it. And remember that a joule is equal to a kilogram meter squared second squared. So that is what that part of it is for. And we do have the velocity, which also needs to usually be in meters per second. And here the mass needs to be in kilograms. So the mass of your particle does need to be in kilograms so that everything in terms of units will cancel out correctly. Because with units here, the kilograms will cancel. The seconds, this second will cancel out with one of those seconds. The second on the bottom will cancel out the other second, and one of the meters will cancel out the meters, and you'll be left with just a meter that's left when it's all said and done. So the good news is it doesn't really change Planck's constant because it is a constant. So you can use it as 6.63 times 10 to the minus 34 joule seconds. You just really have to remember, in most cases, the mass part needs to be in kilograms so everything cancels out correctly. And the velocity of whatever they give you needs to be in meters per second so that it cancels out correctly. So you just got to kind of remember those bottom units need to be there so that they cancel out correctly. So let's take a look at one here. Let's calculate the de Broglie wavelength for an electron that's traveling at 2.65 times 10 to the 6 meters. Let's take a look. So in this case, we're going to use the de Broglie wavelength, which is h over m times v, which is our velocity. In this case, everything's actually in the correct units for you, not always the case. So again, you might have to convert your mass into kilograms. And again, your velocity may not be in meters per second. Again, h is a constant, which is 6.63 times 10 to the minus 34 joules times second. A reminder that a joule is a kilogram meter squared second squared. That means that our wavelength here is going to be 6.63 times 10 to the minus 34. We'll use the other units there, kilograms, meter squared, second squared. And again, that basically is a joule times the seconds that are still there, divided by our mass of 9.11 times 10 to the minus 31 kilograms, and our 2.65 times 10 to the 6 meters per second. Again, in terms of units, seconds cancel there, one more seconds cancel there, 1 meter cancels, and our kilograms cancel, again, leaving us just meters that's left over. Making sure for sure that you are using your exponent button, 6.63 times 10 to the minus 34 divided by 9.11 to the minus 31 and divided by 2.65 to the 6. Going to give us a de Broglie wavelength of 2.75 times 10 to the minus 10 meters. Once again, we just calculated basically a wavelength for a particle, and it can have wave-like sort of functions. And again, that electron being sort of tied to the nucleus, kind of like your guitar string, as it's sort of moving around, and which kind of keeps it there in place, if you will. Any questions on that there? All right, well, it's a good place to stop, I think, for today.